Welcome, ladies and gentlemen. This is the video on the factors affecting the solubility of insoluble salts. This is a final topic in equilibrium, and this is actually the last video that you need to watch for the equilibrium unit. I know, massive cheers going on right now at this point. This is a final topic of equilibrium, which means that it is not nearly as important as the primary or secondary topics, but it does occasionally come up on the AP exam in maybe one or two questions. Is it essential to your understanding of equilibrium? No. Is it an equilibrium topic? Absolutely. It sort of falls, I consider this essentially applied Le Chatelier's principle. So it's a relative of Le Chatelier, and we're going to use the same sort of reasoning here as we did in those questions before. Now, factors affecting solubility of insoluble salts. What am I talking about? Essentially, the idea that our insoluble salts, so we're talking KSP problems, absolutely KSP problems, those things, those compounds that do not dissolve well, how can you change how well they dissolve? How can you increase the solubility of insoluble salts? That's what this is getting at. How can you make those insoluble salts dissolve better? And there are going to be two main ways that we're going to discuss in this video that can increase the solubility of insoluble salts. The first is a question of pH. And you have to think about the cations and the anions that are in your insoluble salt, in your KSP problem. If one of your cations or anions is acidic or basic in any way, then changing the pH of the system will alter how well that KSP reaction works, how well it dissolves. If the substance has a basic anion, as it says here, then it will be more soluble in an acidic solution. Well, why? Because bases react with acids. So if your salt, your KSP, for example, what's shown here, I'm just going to make this a bit bigger, but the salt that's shown here is magnesium hydroxide. Does this have a basic anion? Yeah, the hydroxide, really big one, right? OH. It has a basic anion, so it will actually react with the acids if we lower the pH and help make the magnesium hydroxide go into solution. And then the opposite is true. If we have a salt that has an acidic ion, typically a cation, because, you know, acidic, so H+, so we look for something that would be positively charged, then it's going to be more soluble in basic solutions because acids react with bases. Now, how that works, how that increases the solubility, is what we're going to be talking about on the other page, but that's what we want to think of. Now, remember, our definition of acid and base is a lot broader than it used to be in Regents chemistry. So we are thinking about the hydrogens, having an excess of hydrogens for an acid, but for a base, you have to remember and think about conjugate bases of weak acids, because now we've got a whole mess of anions that are definitely weakly basic, things like carbonate, things like phosphate. Those ions are basic, and so you change the pH, you are going to impact the solubility of these ions. So don't just think hydroxide for basic anions. Think conjugate bases of weak acids. The effects that we have here on pH. Consider the solubility of magnesium hydroxide in an acidic solution. So this is our KSP, a KSP reaction right here. And magnesium hydroxide is insoluble. It's not part of the B for hydroxides on the periodic table. So most of it is going to be over here. Most of it is going to be magnesium hydroxide solid, and only a little bit of it dissolves into magnesium ions and hydroxide ions. Now, I chose magnesium hydroxide for a very personal reason. When I used to work in a research lab, my lab was a DNA lab, and so I worked with DNA, looking at different constructs about DNA. And the magnesium ion is actually a really great stabilizing agent for the DNA backbone. It can basically form some ion-ion interactions with the phosphate backbone, which is highly negatively charged. So the +2 charge on the magnesium helps keep that DNA helix where it should be. Magnesium works better than other things because it's so small, so it can easily get in, and it's very highly charged, so it can get into that small space really, really well. So we needed a magnesium hydroxide solution. I needed to get magnesium hydroxide to dissolve. Well, the first time I went to go make my magnesium hydroxide solution, I added some MgOH2 into a container and some distilled water, and I stirred it. And it didn't dissolve. And then I stirred it some more, and it didn't dissolve. And I kept on stirring it, and it wasn't dissolving. It wasn't dissolving because it's an insoluble salt. It doesn't dissolve. It doesn't dissolve well. Only a tiny little bit of it dissolved well. And then I read the protocol, the sort of how do you get it to dissolve. And it said, adjust pH to a pH of 4. Make the solution acidic. Okay, so I did that. I added some buffer, actually, not just straight up acid, but I added some buffer. I adjusted the pH to a pH of 4, and then magically, all the magnesium hydroxide dissolved. So how did it do that? Because of a second reaction. If you adjust the pH for these insoluble salts that have an acid or a base as part of it, you have a second reaction that occurs. And this second reaction is a neutralization reaction. Right? Neutralization. You'll notice that this is a one-way, meaning it really loves to go in this direction, meaning that it's not really in equilibrium. That water doesn't really turn back into hydroxide and H+. So we add an acid, and that acid reacts with hydroxide. Where is that hydroxide coming from that that acid is reacting with? It's coming from here. So this OH minus that we're getting from the magnesium hydroxide, we add an acid, that OH minus becomes the reactant in a second reaction. It gets used up to be turned into water. Well, let's think about that in terms of Le Chatelier. What did we do to this first reaction? We removed some product. Le Chatelier says, you remove product from a system that's at equilibrium, which direction are we going to shift in? We are going to shift massively to the right in that original reaction. So by doing a second reaction that uses one of the products for the first reaction, we can get the first reaction to go more to the right. By taking that hydroxide right here, and saying, I'm going to use it up by doing another reaction that I know it's going to be involved in. By adding this acid, I'm going to effectively remove it from the first reaction, which will cause a shift to the right. And then what will that do to the solubility of the magnesium hydroxide? It'll make it way more soluble, because this is the side that it's soluble on, right? Aqueous, aqueous. So you're going to take that solid, you're going to encourage it to dissolve by removing one of the products. This is essentially saying these problems are essentially Le Chatelier problems. How do you get an insoluble salt to dissolve better? Remove a product. Cause a shift to the right. Do something that makes the reaction shift right. Along that exact same idea, we can use the concept of something called complex ions to also get our insoluble salts to dissolve better. A complex ion, by definition, is well, it's called complex for a reason. It's not a simple ion, so it's not just one atom that became an ion by gaining or losing electrons, and it's not a polyatomic either. It's something that we get by taking a metal cation, so that's kind of an important bit. We need a metal cation that is surrounded by these other things. They could be molecules, they could be ions, but they're always bases. And when that metal cation is surrounded by these other bases, they're called Lewis bases, which is a definition we haven't seen. Simply know that basically this is why you would tell me that FeCl3 is slightly acidic. You're telling me that FeCl3 is slightly acidic because what ions did it come from? It came from the Fe plus 3 and then the Cl minus ion. Cl minus is neutral, but Fe plus 3 is actually slightly acidic because its conjugate base is a weak base. Metal ions are transition metal ions are slightly acidic, and they can react obviously with things that are bases. And the combination of the two together forms these complex ions. Now, they're complex because they don't form to neutralize charge. They actually carry a charge, and they tend to combine in a slightly weird ratio. This right here is a listing, this table is a listing of common complex ions, and essentially they're formation reactions. So if we look at the very first one, we see we've got the silver ion. So this is weakly acidic, and it combines with ammonia, and that's a base, and then it makes this thing right here, and that's what's called the complex ion. It's complex because it's not simple, it's the sort of weird thing that's involved. It's the silver and the ammonia together, but it carries an overall charge. Now the charge that it carries, you'll notice the silver is +1, the ammonia is neutral, it doesn't have a charge, so basically what's +1 + 0, obviously it's going to be +1. Something else that I want to point out, this right here, Kf, that stands for formation. So we're talking about the formation of complex ions. Look at all of these Kf values. What do you notice about them? Hopefully, the first thing that you notice is that they're all very large. These are very large numbers. These numbers, K is a lot greater than 1. I mean, the smallest one here is that one, and that's 5,000. So that is the smallest K value. We have enormous ones. I mean, look at this, 1 × 10 to the 42nd. Douglas Adams would be very pleased. These are very, very, very big values. So this reaction, that's saying that this reaction strongly favors the formation of a complex ion. That if you have a metal ion and these bases in solution, it's highly likely that will form this complex ion and it won't go backwards. K is much bigger than 1, meaning products dominate. You've got a numerator that is substantially larger than your denominator. The products are in the numerator. So this formation of complex ions, it loves to happen. The other thing that I want you to notice about these complex ions is there tends to be a pattern to how the complex ion is formed. And it's right here. So we'll take the silver one first. The charge in the silver is +1. There are 2 ammonias that form with it. The next one, charge in the silver is +1. There are 2 cyanides that form with it. Charge in the silver is +1. On the third one, there are 2 thiosulfates that form with it. Next one, the charge in the cadmium is +2. There are 4 bromides that form with it. I'm going to skip this one because it doesn't fit the pattern. Charge on the cobalt is +2. There are 4 thiocyanates that form with it. Charge on the copper is +2, 4 ammonias. Charge on the copper is +2, 4 cyanides. That one doesn't fit. Iron, that one doesn't fit, but this one does. Iron is +3, 6 cyanides. There tends to be a pattern where you take the charge on the metal cation, double that number, and that's how many of the bases attract to form the complex ion. There are way more complex ions that can form. As you see, not all of them fit this pattern. So I'm not saying that this is the only way that we form them, but it is the most common way that complex ions are formed. If you are ever, and I don't think you will be, but if you're ever asked to write a reaction for the formation of a complex ion and you don't know how many of your bases you have to add, this rule of thumb will always work. Take the charge in the metal cation, double it, that's how many bases you're going to be adding. Now in terms of determining charge on the complex ion, we'll just take this cadmium and bromide example. Overall charge, basically how do we work out that charge on that the complex ion has overall? Well, the cadmium overall is +2, and then we're adding 4 bromides. Each bromide is -1, so that's a -4. So this -2 is coming from the +2 on the cadmium, the -4 total. Overall, the complex ion carries a charge of -2. Why am I talking about complex ions? Okay, Okay, going through this. Oh, we'll talk about this example too, because complex ions greatly impact the solubility of insoluble salts. So again, this is looking at, so this slide right here is just simply looking at the pattern for the formation of complex ions. If we have the iron 3 ion and we're putting it in cyanide. Cyanide is a weak base because it's the conjugate base of a weak acid. So the complex ion that we would form would be one iron, right? We see just the one iron right here, and then we have the 6 cyanides. So that's the doubling, right? We want to take this, we want to do 3 times 2. So we're doubling the number of cyanides, and then figuring out overall charge, the overall charge of -3. Well, it's each cyanide is -1. So we've got +3 on the iron times 6 cyanides, overall charge of -3. And then the silver with excess ammonia. Silver, that's Ag +1. Charge in the silver is +1. So I want to double it. So I want to have 2 NH3s being added with it. So that's where the 2 is coming from. And then looking at overall charge. Overall charge is going to be +1 because the ammonia doesn't carry a charge. And then the last thing that I want to point out about this before we talk about how this impacts equilibrium, this word right here, excess. Excess. That's how we know if we can get these complex ions to form. These complex ions don't form under normal circumstances. Basically, you have to have a lot of your base. You've got to have a lot of your base. So if we have excess ammonia, if we have excess cyanide, if we have excess phosphate, if we have excess bromide, if there's language to that extent in the question, then we know that we have that situation where we have enough of those things to kind of surround the metal ion and form this complex ion. Now, how do these affect equilibrium? The formation of complex ions will greatly increase the solubility of insoluble salts if the metal ion can participate in this complex ion formation. So, as an example, in what this diagram is showing, silver chloride, which is what's shown here, AgCl, silver chloride does not dissolve. It's a solid. It really doesn't like to dissolve. It's very insoluble. But if you want to get that to go into solution, you can manipulate it by forming a complex ion. So it's essentially the same idea, saying the chloride is not going to be affected by a change in pH, but the silver will. The silver is weakly acidic. So add a lot of a weak base and get that complex ion being formed. Weak bases will greatly increase solubility of our insoluble salts. Why? Same reason as before. Consider silver chromate when excess ammonia is added to solution. Solubility of silver chromate. This is our KSP reaction. Silver chromate is a solid. It is insoluble. It does not like to go into solution. Only a little bit of it becomes the silver ion and the chromate ion. But if you dissolve this thing with excess ammonia rather than water, excess ammonia, there's that word, lots of ammonia. That right there is a base. And it loves to form complex ions with transition metal cations. Transition metal cations are the ones that tend to participate in complex ion formation. We get a second reaction that occurs. So this is the second reaction. This is that KF, K of formation. And remember that these KF values were much greater than 1. That's why this reaction is only occurring in one direction. That it just kind of goes in this direction and goes and goes and goes and doesn't stop. The silver ion here can form a complex ion with the weak base because the silver ion is actually slightly acidic. And ammonia, that's obviously a base. So we have our complex ion over here. Where is the silver ion coming from for this second reaction? Because we know where the ammonia is coming from. We're saying we're making this with excess ammonia, so it's essentially just in your beaker. But the silver ion is coming from here in that first reaction. We're taking that silver ion and we're moving it to be the reactant in a second reaction. what that does is effectively remove a product. You are taking your silver ion out of the first reaction and shoving it to be a reactant in a second reaction that loves to go to the right. That second reaction doesn't go backwards, really. It just goes to the right and goes to the right and goes to the right. So you're using it up. You're removing that product. That causes a massive shift to the right in this first reaction, which then increases the solubility of the AgCrO4 solid. You're causing it to dissolve. You're making it dissolve way more than it did in the past. So we just say, and I'll erase that formation, but the consumption of the silver ion into the complex ion increases the solubility of that silver chromate in that first reaction. That first reaction is where the solubility lies. You're taking a solid and turning it into an aqueous solution. That's the solubility. And by removing a product from that, you're getting that silver chromate to go into solution far, 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 far better. This is really just applied Le Chatelier. This is really both of these things, how pH affects the solubility of insoluble salts and how complex ion formation affects the solubility of insoluble salts. Both of them work the exact same way. Both of them are predicated on the idea that if you perform a second reaction that is very favorable in the forward direction, that just goes and goes and goes in the forward reaction, but uses a product from that first reaction, then you can effectively remove a product from a reaction that is less likely to happen. By removing a product, Le Chatelier says, you are shifting to the right. You're getting that first reaction to occur more than it wanted to because you are basically upsetting the equilibrium. You are removing a product. So both of these work that based on that idea. So changes in pH and complex ion formation, which is essentially just acid-base chemistry, just using metal cations and weak bases rather than strong acids and strong bases, will both cause our insoluble salts, if they have an ion that can participate in them, to be more soluble than they would be in regular distilled water. So you change the nature of the solvent, you're going to change how well it dissolves.